Hello students, this is Dr. Anita Raj, your chemistry mentor, welcoming you for one more session in solid state. Today let us see what is packing efficiency or packing fraction in SCC, FCC and BCC. By the way, what is packing efficiency or packing fraction? See, actually it is the percentage of total space that is filled by the constituent particle is called packing efficiency or packing fraction. Okay. So constituent particles means atoms, molecules or ions. Okay. So those atoms or particles or ions or molecules will be occupying some space, and that percentage of total space that is filled up by these atoms, molecules or ions in a unit cell is called as packing efficiency or packing fraction. Okay. Now that's a formula for this packing efficiency. Packing efficiency is equal to Z into volume of one atom into 100 divided by volume of cube. Okay. Why volume of cube? Because the unit cell will be in the form of a cube. That's why they are taking that as volume of cube. Okay. So what is the volume of a cube? What is the formula for volume of cube? It is a cube. Is it not? For cube, it is a cube, right? What is the formula for determining the volume of one atom? So atom, if they are taking as a sphere, okay, so volume of one sphere is 4 by 3 pi r cube, okay, 4 by 3 pi r cube, right? So that's what written here, 4 by 3, 4 by 3 pi r cube. This is volume of one atom and volume of cube is a cube, understood? Then what is Z? It is the total number of particles you've seen in, if it is SCC, it is SCC or BCC or FCC. Okay, total number of particles present in a unit cell. Understood? So this already I have explained about this how to calculate the total number of particles in a unit cell in my previous video. So I am giving the link in my description box. You can, if you want, you can have a glance at it. Okay. So first we are going to see how to find out the packing efficiency in a simple cubic system. Okay. What's a simple cubic system? We can see the atoms or ions or molecules only at the corners of a unit cell. So then if that is the case, then we call that cube as a simple cubic system. Okay. So now we are going to find out the packing efficiency here. So I have given a schematic representation here. See, this is one corner atom and this is another corner atom, and these are the edges. Okay, here these are the edges. Okay, so what is edge length? It is represented by the term A. So this is A. Okay, this is also A. So edge length. Okay, now this is a corner atom and this is another corner atom, and this is the nucleus of this atom, and the distance between this nucleus and this place is the circumference. Okay, so this is R, and the distance between this nucleus and this is R. Okay, so edge length A is equal to 2R. All right. So before that, would like to tell what is Z here. What is Z? What is Z for simple cubic? It is 1. How will you calculate 1? Because in we are having 8 corner atoms, is it not? Now this unit cell will be in, this corner atom will be in contact with 8 other unit cells. Okay, if so, this corner atom will be shared by 8 other unit cells. So in that case, how many number of corner atoms are there? 8 corner atoms, but each corner atom will be shared by 8 unit cells. So 1 by 8, that's equal to 1. This is how we will be calculating Z. Okay, now what we are going to see from the figure. Okay, from the figure it is clear that A, that is edge length A, is equal to 2R, is it not? So it is R plus R, so 2R. A is equal to 2R. Okay. So what is R? R is equal to A by 2. Students, what is R? It is the radius. Okay, radius. Okay. What is A? It is the edge length. Okay, it is the edge length. Now we are going to calculate the packing efficiency for this simple cubic system. Okay. So what is the formula? Z into 4 pi r cube, is it not? 4 pi r cube into 100 divided by 3a cube. Okay, this is the general formula for packing efficiency. Now we are going to substitute the value of Z here, then R value and also the a cube. Okay, so this we are going to substitute for Z and a cube. This R we can keep as such because in A itself we will be getting R, so that we can cancel easily. So just I am going to substitute the values now. What is a Z? It is 1. 1 into 4 pi r cube. You can write r cube as such. You don't want to substitute a by 2 here. You can write r cube as it is because you can easily cancel that. Okay. So 3. What is a now? What is a? It is 2r. Okay. So how will you write? Into 2. We can write here 2r the whole cube. Okay. Now come on, simplify this. This becomes 4 pi r cube. 4 pi r cube into 100 divided by 3 into what is 2 cube? It is 2 into 2 into 2. Is it not? So 8. Is it not? So 8. This r becomes r cube. Is it not? Now we can simply cancel this to r cube can be cancelled. Okay. So this one and this one gets cancelled. Now this becomes 2. Is it not? 2. So how will you simplify this? Now that's equal to packing efficiency is equal to pi into 100 divided by 6. Is it not? So what is pi value? It is 3.14 into 100 divided by 6. So that's equal to 52.4 percentage. Understood, students? So hence the percentage of space occupied. So the percentage of space occupied in this unit cell is 52.4 percentage. So percentage of space occupied. Okay, percentage of space occupied is 52.4 percentage. Okay. So what is the unoccupied space or the empty space? How will you calculate the empty space in this unit cell? Okay, how will you calculate 100 minus 52? So 100 minus 52.4. So you get the empty space. It is 47.6 percentage. Okay, these things you should be very careful because you should learn thoroughly. You can get this type of questions for one word even. Okay, what is the percentage of space occupied in space cubic, simple cubic? What is the empty space given? Okay, 47.6. So all this you should be aware of. So for SCC, that is simple cubic system, the radius r of the atom is a by 2. That is half of the edge length. Is it not? And the distance between the nearest and the distance between the nearest neighbor is the edge length. Okay, distance between the nearest neighbor. Okay, this okay will be the edge length. Understood, students? Next, we shall see the packing efficiency in face-centered cubic system. Okay, so how this see in face-centered cubic system we'll be having the atoms in the corners as well as atoms in the face. Okay, so we can show here this in face center. In this is one face and this is another face. Okay, and this is another face. So here also we can have, and this is another face. So there also we'll be having one atom. Okay, and now the next face here, is it not? So here also you'll be having one atom. So totally 6 faces will be there, and one more we have at the back. Okay, here also. So there also you can have one atom. Okay, so totally 6 atoms are there in the face. Okay, 2, 4, 6 along with the corner atoms. All right. So what could be the total number of atoms in face-centered cubic lattice? So Z is equal to corner atoms 8 into 1 by 8. See these calculations you can see in my previous video so that you can get a clear-cut idea. Okay. So I'll give the link in the description box now. So next, how many face-centered atoms? 6. Okay. And each face-centered is shared by 2 unit cells. So 1 by 2. Okay. So what could be the answer? 1 plus 3, that's equal to 4. So total Z is equal to 4. Okay. Now we shall take this picture. Okay. Here this is one corner atom and this is another corner atom and this is a face and this is the face centered atom. Now this corner atom is touching the face centered atom and this corner atom is also touching the face centered atom. Okay. Now the distance between the nucleus of this corner atom and the next face center is R, and here we'll be having the nucleus of this face centered atom. So here R plus R, 2R, and again here R. Okay, the distance between the nucleus of this corner atom and this one is R. Okay, and let us have the this one is A and this is B, and let this be C. And what is the edge length? A, and this is A. Okay, now we have got a triangle, is it not? A, B, C. Is it not? We have got a triangle. So in the triangle, see, in the triangle ABC, in the triangle ABC, AB is equal to A and AC is equal to A. Am I right? See, AB is equal to A and AC is equal to A. Okay. But what is BC? What is BC? See here, this BC. BC is the face diagonal. Is it not? This line is drawn. Okay, this is a face diagonal. So this BC is a face diagonal. Okay, so you should be very careful. It's a face diagonal. Okay, now, so according to Pythagoras theory, BC square is equal to AC square plus AB square. Am I right? So according to Pythagoras theorem, see, this is the hypotenuse, right? So this is equal to the AB square plus AC square, right? So according to Pythagoras theorem, so based on Pythagoras theorem, BC square is equal to AB square plus AC square. Understood, students? Now we are going to substitute the value of all these. What is BC, what is AB, and what is AC? What is BC? Here R plus 2R plus R. So totally 4R, is it not? So 4R the whole square is equal to what is AB? What is AB? It is A. So A square. What is AC? It is again A. So A square plus A square. A square plus A square. So this becomes 16R. This becomes 16R square. When you double it, we'll get 16R square. That's equal to 2A square. Now we are going to simplify this. Okay. So this becomes A square is equal to 8R square. When you cancel this, okay, this becomes 8R square. So A is equal to square root of 8R square. Okay. Now see, A is equal to root of 8R square. See, when you simplify this, this becomes 2 into 2 root 2R. Okay, root 2R. So now A is equal to, edge length A is equal to 2 into root 2R. If you want R, what is R? R is equal to A by 2 root 2. Am I right? A by 2 root. Understood, students? Now we are going to find out the packing efficiency. Okay. What is packing efficiency? Z into 4 pi r cube. Is it not? 4 pi r cube in 4 pi r cube into 100 divided by 3a cube. Is it not? So now we are going to substitute the value of z. Okay. We are going to substitute the value of z now and then a cube. So this equation becomes what is z? 4 into 4 pi r cube into 100 divided by 3 into what is A? What is A? It is 2 root 2. Is it not? It is 2 root 2. Okay. So A 3 into 2 root 2 R. Okay. R outside. Now Q. So this equation, when you are simplifying this, you'll be getting, see here, 4 pi r cube, 4 into 4 pi r cube into 100 divided by 3 into, see, when it becomes 3 into 8 into, what is root 2 into root 2? Root 2 into root 2? 2, is it not? Then again one root 2 will be there. So 2 into root 2. 2 into root 2 then r cube. Okay. Now this r cube and r cube gets cancelled. Is it not? This r cube gets cancelled. Now this 4 into 4, okay. This also get cancelled. Finally, it will be 8 and 4 will be getting cancelled. Finally, we will be getting 3 into 2, okay. 3 into root 2, okay. We will be getting. So when after simplifying this, you will be getting pi into 100 divided by 3 root 2, okay. So when you are substituting value of pi, 3.14 into 100 divided by 3 into 1.414, that's equal to 74 percentage. So space occupied, okay, percentage of space occupied will be 74 percentage. So the empty space, what could be the empty space percentage? Empty space is equal to 100 minus 74. That's equal to 26 percentage. Understood, students? So, thus for a face-centered cubic system, the radius of this atom, okay, radius, that is R, will be this R will be, after substituting this, you'll be getting 0.355, okay, times the edge length, and the distance between the nearest neighbor will be, this nearest neighbor will be 0.707 times the edge length. Understood, students? Next, we are going to see the packing efficiency in body-centered cubic system. Okay, what is body-centered cubic system? In body-centered cubic system, you can see the atoms in the corners. Okay, just like the simple cubic and face-centered, you'll be having atoms in the corners. Along with this, you'll be having only one atom in the center of the body. One atom in the center of the body. So this will be having one atom in the center of the body. Okay. Now we can see the schematic representation. See, this is the corner atom, this is another corner atom, and you can see a atom in the middle. Okay. Now this corner atom will be touching the atom in the middle, and this corner atom will also be touching the atom in the middle. That is the body centered atom. Okay. Now the distance between the nucleus of this atom and this one is R, and this is the distance between this nucleus and this one is R, and distance between this and this is R, and this one is R. Understood? So now, now we shall see what is Z. Z for this. Z for this one is 8 into 1 by 8. Corner atom is there, is it not? Plus 1 body center. Okay. So that's equal to 1 plus 1 is equal to 2. Alright. Now let us see this diagram. Okay. This is edge length A. And this is also edge length. BC is edge length A. And this AB is also edge length A. Okay. Now, see, we shall see here. We want to consider a triangle, is it not? AD. We want to. So in this case, it is not possible to take these things. So we need to have a triangle. Okay. So for that, we shall draw a diagonal here. So we have drawn a diagonal here. Okay. Now this is a triangle AC, CD and AD. Okay. So this is a triangle. Now we shall see, when you are taking this triangle A, C and D. Okay. Now AD square is equal to AC square plus DC square. Am I right? See here, check this AD square. This is the hypotenuse for this triangle. Is it not? This is the hypotenuse. So AD square is equal, according to Pythagoras theorem, AD square is equal to AC square plus DC square. Okay, DC square. Right. Now we know what is DC. It is A. Is it not? And we know what is AD also. It is R plus R plus R plus R. So 4R. Is it not? So AD is 4R and DC is A. But we do not know what is AC. So how to calculate AC? AC is nothing but AB plus BC. Is it not? AC is equal to AB plus BC. Is it not? AC is equal to AB plus BC. Okay. Now we are going to write the values, right? AD square is equal to 4R square. That's equal to, what is AC? What is AC? As I told you, what is AC square? AC square is equal to AB square plus BC square. Okay. So we shall write here AB square, okay, plus BC square. AC square, AB square plus BC square. Okay. AB square plus BC square. Okay. Plus DC square. Okay. Here we should put a bracket. Now what is AB square? What is AB square? It is AB square is equal to A square. BC square is equal to A square. Okay. So A square plus A square. What is BC square? It's also A square. Is it not? So now what is this? It is 2A square. Is it not? 2A square plus A square. That's equal to 4R the whole square is equal to 3a square. So when you simplify this, this becomes 16r square is equal to 3a square. Okay. So now we need a square. A square is equal to 16 by 3. Okay, 16 by 3 r square. So a is equal to root of 16 by 3 r square. So when you are simplifying this, this becomes a is equal to, okay, a is equal to 4r, okay, 4r by root 3, okay, 4r by root 3. Okay, a is equal to 4r by root 3. Now we are in need of r. R is equal to of root 3. Okay, root 3 by 4. Understood. So we have found out what is R now, root 3 by 4. Now we are going to find out what is packing efficiency. What is packing efficiency? It is Z into 4 pi R cube into 100 divided by 3a cube. Now we are going to substitute the value of Z. What is Z? It is 2 into 4 pi R cube into 100 divided by 3 into what is a cube? It is, what is a cube? When you are simplifying this, this becomes 2 into 4 pi r cube into 100. See this cube root, okay, will become 3 into root 3, okay, divided by 3 into 4 r cube. Is it not? 3 into 4 r cube. Now when you are simplifying this, this becomes 3 into 4 r cube. Now when you are simplifying this, this becomes 8 pi r cube into 100 into 3 into 3 root 3 divided by 3 into, okay, 64 into r cube. Okay, now see here we have one bracket here. Okay, now this becomes, when you are simplifying this, finally you will be getting root 3 pi divided by 8 into 100. Okay, so finally you will be getting 68%. Okay, now what is the space occupied? Space occupied is 68%. Okay, 68%. What is the empty space? Empty space is equal to 100 minus 68. So that's equal to 32%. Okay, so the radius of the atom R will be this 0.433 times. Okay, R will be 0.433 times that of the edge length. When you are simplifying this value, when you are substituting the value of root 3, here you will be getting 0.433 times the edge length. Okay, the distance between the nearest neighboring atoms will be 0.866 times the edge length. Understood, students? Well, fine, students, you might have understood what is packing efficiency and how to find out the packing efficiency in SCC, FCC and BCC. I shall meet you with another important topic in a short period. Until then, it's Dr. Anita Raj signing off from you. Thanks for watching.